Control and Accountancy for U.S. NRC license applications for liquid fuel MSR. This work was done for the Department of Energy, Office of Nuclear Energy, Advanced Reactor Safeguards and Security Program. The ORNL team includes Karen Ho, Matthew Krupkow, and Rabab El-Zohiri. Let me break down the title a little bit because Material Control and Accountancy for U.S. NRC license applications. So specifically, I'm talking about the domestic safeguards, and it's not intended to address international safeguards or other national regulatory agencies, but some of the concepts might be translatable. Liquid fueled MSR, specifically circulating liquid fueled MSRs, salt cooled reactors may be, from an material control and accountancy perspective, may be more analogous to something like a PBR. So I'm presenting ORNL recommendations that we've come to after thinking about these issues for some time, but I'll say that we're not the NRC. As Karen mentioned, the NRC is on the line, so I would encourage any questions during the Q&A portion for the NRC MCNA group. So it's appropriate to follow Nathan Showman because Nathan really presented the technical underpinnings of the conceptual framework that I'll be presenting today. So BLUF stands for bottom line up front, and this is the statement that sort of encapsulates everything I'll be talking about today. We recommend a general MCNA approach that divides the MSR facility into three material balance areas with item accounting on the front and back ends and version monitoring while the S&M is in process in the difficult to access areas. So backing up for a minute, what is MCNA? It's a system of material control and material accounting measures to prevent, deter, and detect theft or loss of special nuclear material, which is defined as uranium enriched in 235, plutonium, or U-233. So to dig into these two statements here, we're going to get into the details of NRC licensing context for MCNA for MSRs, our recommended approach for MCNA for MSRs, describe performance-based regulation and diversion path analysis, and then present, wrapping up, the conceptual implementation of MCNA for an MSR. Briefly, I want to mention MCNA context for conventional light water reactors. So the requirements for MCNA are found in the Code of Federal Regulations, in particular 10 CFR Part 74, which describes a document called a Fundamental Nuclear Material Control Plan, which must be submitted and adhered to by licensed applicants, except there is an exclusion in 10 CFR Part 74 for utilization facilities licensed under Part 50, which conventional LWR plants are. So conventional LWR plants do not submit this FNMC plan. They still must comply with the other parts of 10 CFR Part 74, like for reporting losses or thefts and record keeping and other things. Part of the reasoning for this exemption is that LWR assemblies are large, heavy items with incapacitating dose rates, so a lot of the theft scenarios are not very credible. The way it works at a conventional LWR is that the fresh fuel assemblies are inventoried, loaded into the reactor, which is sealed for years, then offloaded to a pool. The used fuel assemblies are then counted, and once they're offloaded, that's when the S&M is put on the books using quantities from computational models. So you can see it's relatively straightforward to do accounting because the items are easy to track, but that's not the case for a bulk facility such as a fuel fab plant or an enrichment facility. These facilities have S&M not in item form, but in powder or gaseous form. And so these types of facilities do need to submit FNMC plans, which are hundreds of pages, and they are submitted with the application. They become part of the application. And then significant modifications to the FNMC plan is actually a license modification. So there are new regs that have templates for fuel fab plants and enrichment facilities, but there are not any templates for MSR FNMC plans. At a fuel fab plant, the S&M may change physical or chemical form, but the isotopics remain the same. At an enrichment plant, you do have isotopic change, but you're essentially moving isotopes from one stream to another, and you have a balance over the streams. This is very different than obviously what's happening in an MSR, where you're going to have transmutation and depletion. So you're not likely to have balance of S&M as what Nathan Showman just showed. So MSRs are bulk facilities, and they will very likely need to develop, submit, and implement these FNMC plans. This is our recommended approach for MSRs, which are bulk facilities and reactors. We're dividing the facility into 3 material balance areas. For on the front and back ends, we're doing item accounting, which includes periodic inventories and the inventory differences and the standard errors of inventory differences, and essentially following the Part 74 recommendations. For MBA 2, we are not doing inventories, and we're not recommending process monitoring. Instead, we're recommending diversion monitoring at points that have been identified where material diversion may be possible. So for example, if there's a drain tank where diversion may be possible, drain tank that salt is drained to as makeup salt is added, we would recommend that there be at least 2 independent methods of diversion monitoring at that drain tank to ensure that diversion is not occurring. One of the issues with this approach would be how to draw the boundaries, in particular of NBA 2, recognizing that some facilities might have salt synthesis or holding tanks or other salt processing that kind of straddle the boundaries between the different MBAs. So the different designs will have different subtleties and nuances, but in general, our recommendation would be that the MBA boundary would correspond with the physical boundary that would make access to the material difficult. So while we're not recommending process monitoring on MBA 2, we are still tracking transfers from MBA 2 to 3, which is where the irradiated fuel salt or packaged waste would be. And so in this way, it's sort of analogous to the way things are done at a conventional LWR, where the S&M is put on the books once it's offloaded. We're not recommending process monitoring because it would be difficult at best, as shown previously, and likely not possible, but there are other good reasons. So the material at MSRs, obviously not the same as at a fuel fab or enrichment facility. It is highly radioactive and not easily accessible. Also, process monitoring would be inconsistent with the NRC's approach to other reactor types. And I think it's worthwhile to do the thought experiment and just consider all the parameters necessary to monitor, to perform an inventory over the entire system. Obviously power, feed removal rates, temperature, densities, reactivity control, salt polishing, fission product removal. And as shown previously, the measurement precision and nuclear data are not likely to provide you assurance that upwards of tens of kilograms of S&M could be removed. You could also consider biases from sensor drift or holdup. So even if this were an implementable approach, it would probably be expensive, and we believe it's not really necessary to achieve the goal of MCNA, which is to prevent and detect diversion of material. So while we're not recommending process monitoring, we do need to do something else besides just measuring inputs and outputs between the MBAs, because just measuring those inputs and outputs would not be enough to achieve the purpose of the MCNA system. We have to acknowledge the differences between LWRs and MSRs, not in large, heavy countable items, not stationary and sealed in one location. There is potential for sampling ports or other possible pathways for diversion that aren't present in LWRs. And so without an additional measure, timely detection of material loss or theft would be unlikely. And so we're proposing the additional measure be diversion monitoring, informed by something called a diversion path analysis. Before I describe that diversion path analysis, I just want to mention this concept of performance-based regulation. So this was taken directly from the NRC, and the most relevant part here is underlined, which says performance-based regulation is a regulatory approach that focuses on desired measurable outcomes rather than prescriptive processes, techniques, or procedures. So rather than the NRC being prescriptive about a particular safety system or security system, a performance outcome is defined, and then analysis is done to show that that performance outcome can be met. So in the safety case, one of the tools used would be like PRA, probabilistic risk assessment. Security, some nuclear facilities need to demonstrate they can defend against the design basis threat. And so we're proposing this analogous tool called diversion path analysis that would be used for MCNA. We're suggesting this because the 10 CFR Part 74 requirements and the existing new regs are really tailored towards existing reactors. So we think that this tool could help demonstrate that an MSR is meeting the requirements of the MCNA. So the diversion path analysis identifies potential pathways that S&M might be diverted in each process stream by assessing approximate quantities of S&M that could be diverted, the technical difficulty of the diversion, and then what the indicators of that diversion could be. This process has been carried out here at ORNL in a classified environment for an MSR concept, and subject matter experts created a list of technical objectives. For example, what is technically required to quantify the S&M and use filters from the MSR off-gas system. Again, this is not a normal part of the NRC MCNA development process, but this could be useful to develop an FNMC plan for an MSR. And then the FNMC plan would need to identify those places where there would be differences with 10 CFR Part 74. So now returning to this diagram, but annotated with some system elements of the MCNA system. These elements would be outlined in the FNMC plan. On the front and back ends, MBA 1 and 2, you have gross net weight of containers, transfer tanks, perhaps gamma spectroscopy on the outside of containers for material characterization, tamper indicating devices, basically conventional MCNA system elements. In MBA 2, you have an element that would be inline measurement for transfers to and from MBA 2. And in this particular example, with the drain tank identified as a potential diversion location, there's maybe a level indicator and a net weight of the tank that if there's also a sample line present, there would be some means of quantifying the isotopics and the mass that would be removed through the sample line. So the goal here is to combine the elements in MBA 1 and 3 with the diversion monitoring in MBA 2, such that the NRC would be notified if a real loss or theft occurred in a timely fashion. All right, so again, I have that encapsulating statement up there about dividing the facility into those 3 MBAs, item accounting in the front and back end, diversion monitoring while the S&M is in process in difficult to access areas. We think this satisfies the goals of MCNA without process monitoring and ensures that the diversion pathways are analyzed and monitored. This is consistent with conventional LWR MCA practices and bulk facility MCA practices. So future work on the project is to quantify holdup in used equipment, practical containment and surveillance, and Karen's talk will actually address quantifying S&M and fresh fuel in pipes and tanks. The DOE ARSS website posts a lot of these documents, so they don't have a very concise URL, but if you Google DOE ARSS, you'll find a website hosted at Sandia, and all of these documents are publicly available. But that's all I have today, so happy to take any questions.
Thanks so much, Nick. We have time for one question.
Okay.
He's got it. Let's hear it, Dave.
They already given it. You indicate the NRC only has Part 50 or Part 52 as a method for licensing reactors. Are you recommending rulemaking to change Part 74 to remove the exemption from Part 50 licensed facilities? Because I believe all MSRs, today, as a commercial reactor would need to be licensed under Part 50 and would therefore be under the exclusion. Or are you recommending creation of an alternate licensing path for MSRs, which doesn't use Part 50?
Neither one. So in Part 74, thank you. So in Part 74, there's a section that allows the NRC to make allowances that still achieve the overall goal. So there essentially be exceptions. So I'm not suggesting any sort of modifications to Part 50 or Part 52. The utilization facilities, which are reactors, LWR reactors, they get that exclusion. It's not clear that MSRs would be classified as utilization facilities under Part 50.
I think you're going to have a hard time convincing most MSR vendors they are not a utilization facility license.
Well,
Part 50.
That's not my job.
The NRC is actually on the line, and
yeah, I'd like to hear about that. But I had one other thing on here, which was definition of saying an MSR is a bulk facility. Because one of the characteristics of bulk facilities typically is high throughput. MSRs may have less throughput than LWRs. I mean, several of these designs put salt in and it stays in for decades and it doesn't come back out. And so if it has lower throughput than an LWR and by the time it's out, it's a solid big chunks on here. Why is this necessarily, you just stated that they're a bulk facility as opposed to these are the characteristics that this type of reactor would have to be considered a bulk facility. I would suggest that okay, if an MSR does this, it has characteristics which resemble a bulk facility. If it does this, fuel and pins, for example, considered an item facility, or it might have some characteristics of both rather than just saying MSRs are bulk facilities.
Yep. Great points. I mean, I think that's where the NRC could clarify their requirements and what they're asking for. So, ORNL's role as an R&D organization is to support with some potential solutions. Those are certainly bigger questions than I'd say Nick or I could answer.